Imagine, if you will, the great potential that that arises when we bring together distant viewing and close reading, when we bring together large-scale retrieval that computer vision has to offer and a close-up analysis of the individual samples that we have actually retrieved. I'm lucky to, now for roughly 10 years, had a group that's interdisciplinary, that's rooted in 2 departments, having students and postdocs from math and computer science and so on, but also from art history, 2 of whom you're meeting today. We've been thinking about ways of building retrieval tools, like things that we've seen already, which enable you to detect objects in huge sets of images, but then also reason about the interrelationships and the fine-grained details that there are in these huge corpora. Now, computer vision comes with a huge promise, the promise of acting like a funnel for data. For art history, it means that with these huge, now digitized collections of images, that it promises to provide us algorithms that funnel these data into computers that then present us with answers to hopefully everything that we are asking about. And obviously the algorithm, which is the workhorse of all of that, is deep learning or neural networks. We've seen a lot of examples of that already, so I don't need to talk too much about that part here. And the outcome of that, if you now want to bring together the large-scale retrieval, the large-scale questions of detecting objects, together with a fine-grained analysis of, for instance, where are these objects relative to another? What does that mean that you have a certain gesture in a certain position there in the scene and relative to other objects and so on, get you much beyond just enumerating all of these images. Sabine Lang, who's going to talk afterwards, is going to give you more examples of this search engine, this web-based search system that we have put together, and we are presently in a collaboration with a digital archive called Prometheus of setting that up for them for huge retrieval problems. Another part or another question that you can then answer by bringing together distant viewing, close reading, is, for instance, reception analysis, like we had in the first talk in the second section, where we cannot only find an image and then all receptions of this work, but automatically do a morphological analysis, find out about the fine-grained details by means of which the original and its reception differ, and then think about what these differences actually mean. Now, I'd like to talk about a few basic issues that there are if you just apply the underlying methodology of neural networks here, if you just apply these off-the-shelf methods, and I'd like to provide you at least with a few solutions to these fundamental problems. So stick with me. Lots of deep learning, or lots of the progress that deep learning has shown over the last years, is actually based on having huge amounts of images there from which we can learn. And that's one of the secrets why it took so long for deep learning to really eventually work, although the algorithmics underneath are not that recent. So for training, we need lots of images. Computer scientists have compiled a lot of image data sets, huge image data sets with millions of images from the web. But it's not just images. What you also need are labels, annotations. I mean, it needs to tell you which object classes you see in these images. Now, art historians probably don't care so much about airplanes and cars and things like that. And that's when we want to go to the data sets that we care about, we actually need to do what's called transfer learning. Take the model that has been trained and adapt it, fine-tune it to the very data that we actually care about. Now, the issue with that is it not only requires data, which we now have tons of available, it also requires, again, annotating this data. Because we're not interested in airplanes, we might be interested in crowns and other things that people stick to their head, and these classes are not available in ImageNet. So you need to, again, label data, and because that's a really tedious task, we cannot go for the entire data, but only for tiny subsets. Tiny subsets, fine-tune the model on that, and that's all fair and well. Transfer learning then means that you, once you've trained the model, apply it to the entire data, and then infer labels, whatever you're interested in, on the entire data. Now, this is all okay, and my group has done a fair amount of work on transfer learning ourselves, and I like this part, but from an art historical point of view, I was really thinking about, like, where does this lead, and where are issues with that? Because Einstein said here, yeah, you should not stop learning, right? I mean, in a way with transfer learning, that's exactly what we do. You train just on a subset of the data, and then the training is done. After that, you freeze the model, and you just infer and apply it to the data. Now, if you think about an art historian dealing with a new data set, you're learning each and every day. It's really like lifelong learning. Each new image that comes in teaches you in a way something new. It's not that your whole idea of the world changes, but you adjust with time. And isn't that what we also want with a model, rather than freezing it after showing it just a few images and then just like applying this off-the-shelf algorithm? Don't we want it to adapt and change like its viewing paradigms away from ImageNet, which is just adjusted to some Flickr data set, to something which we actually care about, and learn then on the entire data set? Second issue, all of computer vision, as well as all of what we're doing in art history, is actually built on the concept of similarities and dissimilarities. It means we need to reason about relationships between objects, need to reason about relationships between scenes to then do detection, categorization, grouping, and all of these other tasks. And then answer the final question that gestaltists like Kurt Kofka already told us about, like, why do things and scenes look the way that they actually do? For that, you need to understand about similarities. The problem with similarities, however, is that they are quite tricky, that a lot of, or most of the similarities are in fact unreliable. So if you take a medieval crown, which here's kind of lost, medieval crown, and let me just go back again. Okay, that's supposed to be a crown here, and find other related objects, then somehow this slide is broken, then you will, fair enough, and order all of these other detections here according to their similarity, then you will have an easy time finding a few other crowns which are almost duplicates of what you have. And in case you could see it, you will have an easy time also finding quite a number of crowns which are definitely dissimilar. But the problem is, if you order all of your detections according to their similarity, the middle part here, the hugest part of all, is totally sort of unordered. You will have crowns which are related, and then followed by some which are unrelated, and again, and again, and again. So the problem is, we can find a few similar and a few dissimilar items which are reliably similar and dissimilar, but the majority of the relationships are just unreliable. So what's the way out? The way out, so that you can really utilize all the data without annotations for training, would be what's called self-supervised approaches to metric learning. Metric learning meaning like learning similarities, which means you take a few data items, the crown that you were starting with, and a few crowns from here, the highly related entities, and A, in that case, the crown that you're starting with is a friend of B, B is a friend of C, so A and C should also get along, or the others should reason about their friendship that they have. So these transitive relationships are what you want to utilize to then extend away from these tiny sets into this area. We have absolutely no clue about their relationships. So try to keep it short here. This crown, which is again lost for whatever reason, is one which you can randomly pick. So all of your data is here, this huge black cloud. You pick just one entity, and then by means of these few reliable, and here in green, and a few unreliable data samples that you have, you try to bootstrap yourself, reason about their interrelationships so that you can grow this set of reliable data samples. And with that, we've actually went further and replaced the annotations that you require down here and just utilize these similarity and dissimilarity constraints to bootstrap ourselves, find more related entities, more unrelated entities, and then extend this area of reliabilityness and shrink this reddish area that we have up there. Okay, we're not done with similarities though, because if you look at what makes things dissimilar and what makes things related, it differs a bit from kind of our Google way of things. We just type in a query and you find all of the things automatically which are related. Yeah? Like just a one-dimensional listing. I think that there kind of our mindset is just like too much stuck in the digital age, because what's actually true is if I reason about persons, for instance, human beings, then there might be a lot of different axes according to which you can sort them according to their dissimilarities. They might differ in terms of their posture, they might differ in terms of the viewpoint under which they have been painted. Besides these shape-based relationships, there's also appearance-based relationships, color of skin, the texture of the clothing that they have. And then it can go all the way again, even to iconological relationships, things beyond just like young and old, but for instance, rich and poor. After all, who is richer in that case? The king who's soon to die, or the person who's holding the treasure on their arm? And what we've now done is concentrate on mainly the shape-based relationships and the appearance-based relationships, and build a search system which is not just like mingling all of that together and giving us a bunch of queries ordered by some arbitrary sort of mixture of all of these similarities, but giving the user then a direct sort of folding up of these similarities and understanding if something is related based on the shape or the appearance. For that, just like a brief shot at what's going on. Unfortunately, these images, like when we did the check, they were all there. Now they're kind of all gone. Yeah, okay. So what you were supposed to see, and last time I was standing up here, was still there, was that you can utilize a fixed appearance as input, and you can utilize a fixed shape, another image showing a shape as an input, and then generate additional images, which you were supposed to see here, additional images for which you can here see the inferred posture of these images, which the machine has never seen beforehand. So you then generate, by just presenting a bunch of persons which differ in their appearance and giving a single fixed appearance, generate other persons in different shapes there. Okay, at least you can see this video giving you a clue of that. So you here fix the appearance. Here you go for different postures, and these here are all synthesized by a neural network, things which haven't been there beforehand, giving us an idea of how we can independently synthesize posture and synthesize shape. Now, if we are able to do that, then we can actually turn the process around, utilize that to learn relationships, shape-based and appearance-based relationships. And what that enables us is to go across different techniques for painting, to search across different receptions, for instance, of the same piece of art, maybe even across different media, and have a robust retrieval tool which can then search really for the content of the scene. Last thing. The last issue is really this question of, should I just search for an entire scene or a bounding box? If I give you an object that I have cropped from a painting, I ask you, what is this? I guess you kind of have a hard time reasoning about what this is, although it's magnified. So size is not an issue. But if I give you the context of the entire scene, then you have this idea of, okay, this here being like ocean and water, there being a lot of boats, and sure enough, this thing here is a rowing boat. And you might even start wondering about how many people are there sitting in the rowing boat. So the story here is recognition is more than just observing individual pixels. Recognition is more than just thinking about an individual bounding box or the entire object. It's about partonomies that you have in this scene, about contextual relationships. And that means that when we build a retrieval system that kind of went into this web-based system that Sabine will give you a few more examples about afterwards, when we built our retrieval system, we were, sure enough, starting with queries, which is like, okay, this is the entire image, it's a still life, find me other objects which are similar, and yeah, sure enough, you find other still lifes, but that might not be what you're actually looking for. Okay, so you go for a bounding box, right, and you take this skull here and you find other scenes where this is, but that's probably also not what you're looking for. What you want is an approach that enables you to select several parts, have a slider where you can adjust how rigid or how relaxed the spatial relationship between these parts is supposed to be, and then find other still lifes with exactly all of these objects in there with a more or less relaxed spatial change of the spatial geometry. So let me wrap up. I think computer vision has great potential for turning images into what can be called like first-class citizens of data processing, much like what we are now kind of pretty happily using with text. So text, you type in Google, you search, you analyze that, and so on. For images, similar abilities are still somewhat lacking, but computer vision has the potential to get us there. However, with just the off-the-shelf methods, you can come quite a way. But if you want to do a real detailed analysis, I think there are a few things that we should actually take care of, and that is handle the unreliable relationships that they are in. So far, typically you just assume that everything is fine, and you throw all of them in and get a single TSNE plot, and just hope that these relationships, which you think like few relationships which are broken in between don't hurt you, but it's actually the majority of the relationships which are broken, so that actually hurts your low-dimensional embeddings. I think we should go beyond the supervised learning, which was the workhorse of everything that we did beforehand, and utilize the vast amounts of data that we have, squeeze out everything that we can, and then we should consider the multivariate nature of similarities and explicitly model like different ways that images can be similar and dissimilar. And lastly, reason about several parts, their relationships, partonomies, and contextual relationships. Thank you for your attention.